On September 10, 2025, SpaceX's Starship, the largest and most powerful rocket ever constructed, thundered off the launch pad for its historic 10th test flight. This was not just another launch, it was a moment that captured the imagination of millions around the globe, a testament to human ingenuity and the relentless pursuit of progress. The world watched in awe, not only for the spectacle of liftoff, but for the challenge that lay ahead, the return. This was the true test of reusability, a concept that could redefine the economics and possibilities of space exploration. After reaching its target altitude high above the Earth, Starship began its carefully controlled descent, bracing for the intense heat and forces of re-entry. The spacecraft's heat shield glowed as it sliced through the atmosphere, a fiery trail marking its return. The challenge has always been not just getting to space but coming back safely. For decades, engineers have grappled with the dangers of re-entry, knowing that a single miscalculation could spell disaster. Starship Flight 10 demonstrated a bold solution, the now famous belly flop maneuver. By using its broad underside to slow its descent from hypersonic speeds, Starship turned the atmosphere itself into a brake, showcasing a new era of aerodynamic control. With remarkable precision, tiny adjustments from its fins guided the rocket's path, transforming what could have been a catastrophic fall into a graceful, controlled return. Every movement was calculated, every second critical. As Starship neared the ground, its powerful Raptor engines roared back to life, flipping the massive vehicle from horizontal to vertical in a breathtaking maneuver that left viewers holding their breath. This flip and burn maneuver is one of the most audacious feats in modern rocketry, demanding split-second timing and flawless coordination between software, hardware, and human oversight. It's a dance with gravity, performed at the edge of possibility. The vehicle descended slowly, engines firing in perfect harmony, before gently touching down on the landing pad. A triumphant conclusion to a journey fraught with risk and uncertainty. Starship's ability to launch, land, and be readied for another flight in rapid succession is a paradigm shift for space travel. It promises a future where rockets are no longer single-use, but reliable vehicles, ready to fly again and again. Unlike the space shuttle or parachute capsules of the past, Starship's full reusability is a dream realized, a vision that has inspired generations of engineers, scientists, and science fiction writers alike. Flight 10 was not just a test, it was a turning point. It proved that routine, affordable access to space is no longer a distant hope, but a goal within our grasp. Each successful landing brings us closer to a world where space travel is as commonplace as boarding an airplane, and where the next generation can dream even bigger. Starship Flight 10 was more than a technical achievement, it was a giant leap toward humanity's future among the stars. Even in triumph, spaceflight reveals its challenges. Every successful mission is a testament to human ingenuity, but also a reminder that the path to the stars is paved with obstacles yet to be overcome. As Starship re-entered Earth's atmosphere, it faced searing plasma at over 1,400 degrees Celsius. The friction and heat generated during re-entry create one of the harshest environments any spacecraft can endure. Its thermal protection system, thousands of black hexagonal tiles, shielded it from the inferno. Each tile is meticulously designed to absorb and deflect the intense heat, forming a protective barrier between the spacecraft and the deadly plasma. Yet, post-flight inspections revealed discolored tiles and small gaps between them. These subtle imperfections are easy to miss, but they can have serious consequences if left unaddressed. These tiny fissures are dangerous. Superheated plasma can exploit any crack, threatening the rocket's integrity. Even the smallest breach can allow heat to penetrate, potentially causing catastrophic damage to the vehicle's structure. The cause? Launch vibrations, extreme temperature swings, and aerodynamic pressure during the belly flop maneuver. These forces constantly test the limits of the heat shield's design and installation. Each tile must withstand heat and remain perfectly in place. Engineers rigorously test and inspect every tile, knowing that the safety of future missions depends on their reliability. While minor on this uncrewed flight, such issues are critical for future crewed missions. Astronaut safety will depend on a flawless shield, making these findings all the more important. The data from Flight 10's heat shield is invaluable, pinpointing weaknesses to address. Every anomaly is carefully logged and studied, guiding improvements for the next iteration. SpaceX engineers now know exactly where to strengthen the shield. Their work is a continuous cycle of testing, learning, and refining, inching ever closer to perfection. Every imperfection is a lesson, turning vulnerability into progress, Each repair and adjustment brings the dream of safe, reliable space travel one step closer to reality. The journey to a flawless heat shield continues, driven by relentless innovation and the unwavering pursuit of safety for all who will one day ride these ships to the stars. Building a reliable heat shield is a feat of extreme material science demanding both creativity and precision from engineers. The challenge is not just about withstanding heat, but about finding a material that can survive the harshest conditions spaceflight can offer. Starship's black ceramic tiles are engineered to absorb and radiate away the intense heat of re-entry, keeping the rocket safe. These tiles must endure temperatures hotter than molten lava, all while protecting the delicate structure beneath. SpaceX also experimented with metallic tiles, hoping for greater durability and the potential for easier repairs. The idea was to find a solution that could be both tough and reusable. Metals, while strong, conducted heat too well, creating dangerous hotspots and warping under thermal stress. The tests revealed that even the toughest metals could not prevent heat from reaching the rocket's skin. The experiment proved that insulation, not just strength, is key. A heat shield must block heat, not just survive it, and ceramics excelled where metals fell short. This process of trial and error is the heart of engineering. Each failure is a lesson, each success a step closer to the goal. By learning what doesn't work, SpaceX refines what does. Every test, whether it ends in triumph or setback, adds to the collective knowledge. The metallic tile tests reaffirmed ceramics as the right choice. The team returned to ceramics now with a deeper understanding of what's required for true protection. Now, engineers focus on perfecting the ceramic system, confident in its foundation. Every detail, from tile shape to attachment method, is scrutinized and improved. Each test, even a failed one, is a step forward. Setbacks are simply opportunities to innovate and adapt. The quest for the perfect tile is ongoing, but the path is clearer than ever. With every iteration, the team gets closer to a heat shield that can be trusted on every mission. Every lesson brings Starship closer to safe, routine re-entry. The dream of reusable, reliable space travel depends on these breakthroughs. Progress is built on discovery, and with each experiment, SpaceX moves one step closer to making history. With ceramics confirmed, SpaceX engineers tackled the next challenge, sealing the gaps between tiles. The solution, a new wrapping technique, fills gaps with a flexible, heat-resistant material, then covers seams with a thin, durable layer. This process, tested on Ship 37, involved rigorous ground trials, simulating launch and re-entry conditions. The results were promising, sealed gaps stayed intact, and the wrap held strong. This innovation transforms the shield from a patchwork of tiles into an integrated thermal barrier. By sealing the gaps, SpaceX fundamentally improves the shield's resilience. The success of Ship 37 gave engineers confidence to implement this method on future flights. It's a classic case of iterative design: identify, solve, test, and improve. Each step makes Starship safer and more robust. Every test flight is a lesson, and Flight 10's data is shaping Starship Flight 11, the most significant upgrade, full implementation of the new heat shield wrapping technique. Engineers expect this to eliminate gaps and prevent plasma penetration. Software and Raptor engine upgrades informed by Flight 10 will further refine control and reliability. Each flight tests not just the rocket, but the entire system. Flight 11 embodies SpaceX's philosophy: learn, iterate, and perfect. Each success brings interplanetary travel closer to reality. For decades, spaceflight meant building rockets for single use, an unsustainable model. Starship changes everything with full and rapid reusability. Both the booster and spacecraft are designed to return, land, and fly again, slashing costs. This economic shift makes ambitious missions, space stations, lunar bases, Mars cities possible. Reusability is the gateway to becoming a multiplanetary species. Each Starship landing is a step toward routine interplanetary travel. This is how we'll build a new branch of civilization beyond Earth. The future of humanity depends on it. While Starship points to Mars, Falcon 9 is transforming space access today. Its reusability enables vital scientific missions like NASA's IMAP and SWFO-L1, which study the Sun and protect Earth. SpaceX's partnership with Firefly Aerospace will deliver payloads to the Moon and deploy orbital tugs for satellite transfers. These missions build the infrastructure and knowledge for humanity's future in space. From landing rockets to studying solar winds, each mission is a piece of the puzzle. Together they move us from observers to active participants in the cosmos. The tapestry of exploration is growing. Our future among the stars is being forged now.